So here is our Apollo-style spaceship that we will be launching in order to simulate a trip to the moon and back to Earth again. That was done through the game Kerbal Space Program, and here it is. So, first step is to achieve orbit around the Earth, and to do that you have to basically accelerate to a speed at which they get an orbital velocity, which, as you'll see later in the video, is around 7 kilometers per second, depending upon your altitude. So we're going for a parking orbit around 300,000 meters, so that'll mean an orbital velocity around 7,000 meters per second, tangential to the Earth, the curve of the Earth that you are above. The velocity of an orbiting body, where one body is much less massive than the other, is actually equal to the square root of the gravitational constant times the mass of the object being orbited, divided by the distance from the orbiting object to the center of the mass of the object being orbited. So in this case, it would be the distance between our ship and the center of the Earth as the center of mass. And the gravitational constant is just a constant, and the mass of the Earth is very, very large, so our ship is insignificant compared to it. You don't need to include it in the calculations. Now, there are a couple of things of import happening during this ascent. One is the angle at which I'm ascending. You can't just... The ideal way to reach orbit would just be to tilt over to 90 degrees and accelerate in that direction, because that would be moving in the same direction of the Earth's rotation, so that you could add the rotation of the Earth to the orbital velocity you eventually need to achieve. However, can't do that in this case because the plane of the orbit of the moon is not along the equator of the Earth. It's tilted around 30 degrees. So we have to offset our orbit that we're trying to achieve by 30 degrees to be within the same plane of the moon. That makes it much easier to rendezvous with the moon after achieving orbit. So you might be able to tell, as you're watching this, that we're actually almost at a orbital velocity, around 7,700 meters per second, and going to be turning off the engines pretty soon, so we can be at a nice stable parking orbit of around 300 kilometers above the surface of the planet. There we go. We are now officially in orbit. So next up we will be separating from the previous stage that got us into orbit, and now all it is the payload that we will be using to get to the moon and also to land on the moon, and then the rocket that will propel us to a rendezvous with the moon, which is at the bottom part of the ship. So the next step is to figure out exactly how much velocity change I need to apply to this orbit to basically raise its apoapse so that it intersects with the moon's orbit. So I'll show you exactly how to do that. But basically what we're going to do is accelerate on one side of this orbit, opposite to where we want to extend the orbit on the opposite side, right? So I'll show you with a maneuver node. Basically, as you accelerate, which is what I'm doing when I pull that edge, it brings out the opposite side of the orbit. So whenever you accelerate in a forward direction towards prograde is what it's called, accelerating towards your direction of velocity, you increase the opposite side of the orbit outwards until, as you can see here, I have an intersection with the moon, so that when I get to the point on the edge, the moon will also be near enough so that the gravity from the moon will pull me towards it. And that's basically my goal. On the bottom you can see exactly how much change in velocity, which is delta v, and that's how much I need to change my velocity in order to make this orbit change occur. So what follows is just me changing the direction of the nose of the spaceship so that the thrusters are faced in the right direction, so that I can actually accelerate for that maneuver node to reach the orbit that I want to end up in so that I intersect with the moon eventually. So I just have to do the whole burn, and I'll cut until the next stage. So because this is a Apollo style spacecraft, we actually have the entire service module and lander inside of a fairing on top of the ship, which we have to open up as seen. And the lander is actually in the bottom section, and the service module is above it, with a docking port on both ends. So we have to detach the service module and turn it all the way around and have it dock with the lander, which takes quite a bit of time. So I'm going to fast forward through that. So what I'm doing here is activating the antenna that will communicate with Earth after I get farther away. And also, after activating that, I had to make a correction to my course so that I would end up on a equatorial plane when I reach the moon, because if you can see, my original trajectory put me way above the moon and would put me into like a polar orbit. I wanted more of an equatorial one. Makes it easier to land and to do other maneuvers. So to do that, I had to basically burn south. If you imagine like a polar axis through space relative to the Earth, so I had to burn southwards when I reached what's called a ascending node, which is, if you imagine two interlaid circles, one upon the other, the ascending node would be where the circles touch if they were offset. Each circle is a different orbit, and if they're offset, then they only actually touch in two different points. Those are the nodes, and those are the only 2 points at which you can turn the circle so that the two circles will line up and be on the same plane as each other. And that's what I had to do. So after fixing that, I flew the ship for a while, making small corrections that I could end up exactly where I wanted to, and eventually I reached the moon, as you can see here. So once I reach the moon, I'm actually moving much, much faster than I want to. I'm gonna shoot right past it and not enter a stable orbit. And after that, I'd probably shoot off into space, into, I don't know, some orbit around the sun, leaving the Earth behind. And I obviously don't want that, so I have to slow myself down by accelerating in the direction opposite to where I'm going, which is called a retrograde acceleration. So burning retrograde, and that brings my orbit down towards the moon. So now that I've reached this stable, low lunar orbit around 100,000 meters over the surface, I can start the next step, which is to detach the lander and drop down onto the moon. So here is the lunar lander separated from the service module and the rest of the ship. So as you can see, it's making its descent towards the surface of the moon. Now in order to do that, in order to deorbit the lander, I have to burn retrograde, which is the same thing I did when I was trying to make the stable orbit around the moon. Basically slow myself down relative to the surface of the moon. This allows gravity to pull me down to the surface so that I will eventually land. Now, the tricky part is to continue accelerating upwards to negate gravity so that I don't crash into the surface of the moon, but at the same time not apply too much thrust so that I go back into orbit. So you might be able to tell that I'm actually going very quickly relative to the surface of the moon, even though I'm just above it. And this is the first attempt, and I actually failed this landing, ended up toppling the lander over. On my next attempt, I was much more successful. Here's the first part was just the same as the first, and here's the end of it, where I successfully decelerated and landed on the moon. Here you can see the Earth in the background and our flag planted upon the moon, claiming it for all of Kerbal-kind. As you can see, here's our lunar lander, and there's no point in actually bringing the landing legs and all the extra stuff back into orbit, so we have this small ascending module that is just meant to bring the crew back into a stable orbit to rendezvous with the rest of the ship and make its way back to Earth. Sending from the moon is basically the same as trying to get into orbit of Earth, except that instead of trying to match planes with the moon as I did when I ascended from Earth, I'm trying to match planes with the service module that I left in orbit so that I can dock with it once I'm in a orbit over the moon. The next stage is actually to make a rendezvous with the service module over the moon. Now, this is actually pretty difficult because obviously the service module doesn't have a substantial gravitational pull that I can use like the moon did to help me reach it. So instead I have to basically adjust my orbit precisely so that after a certain number of rotations around the planet I will meet up with the service module. Now I can do this because of how orbital mechanics work. Basically, kind of counterintuitively, when you accelerate on one side of the orbit, you end up bringing the opposite edge of the orbit farther away from the planet, which makes sense. However, which makes less sense, and is also true, is that that slows your overall orbit, making the time it takes to get all the way around the planet longer, basically increasing the orbital radius and major axis. So I can use that to have a slower overall orbital speed or orbital period than the service module, so that the service module can catch up to my lunar ascension module, and then I can rendezvous with it. So you can see here the service module and lunar ascension module have met up and are slowly approaching each other. Now this is basically can correct the course by shooting small jets of gas in the opposite direction where you want to accelerate, and that allows you to precisely meet the docking ports together. After meeting up, we can transfer the crew from the lander into the service module and then leave the lander behind in orbit of the moon, where it will stay for a very, very long time. And from there, we send the service module back to Earth. This is, in a way, the opposite process of what we did before. Much easier, because instead of having to actually rendezvous with the moon, instead all we do is accelerate away from the moon in a direction opposite its direction of rotation around the planet, which gives us a smaller orbit than the moon, because we're actually slowing ourselves down relative to its orbit by the time we leave its sphere of influence. From there, we simply do the same thing as before when we tried to land on the moon, but on a much larger scale, in which we accelerate in a direction opposite to our direction of orbit, which brings our periapsis, which is the part of the circle of orbit that is closest to the planet, in this case Earth. So bringing that down to a altitude that's within the Earth's atmosphere, where a reasonable amount of friction with the air will actually slow us down the remainder of the way and allow us to land on the planet. Now, a couple of days later, we're actually nearing the Earth, and as you can see, there's a small red line on the orbital line, and that signifies parts where we're entering into a portion of the Earth's atmosphere where a significant amount of air exists, and that will slow down our ship. If you can look at the orbit, there's a blue line and a white line. The white line represents our expected orbit after being slowed with by friction with the air, whereas the blue line would be if there was no atmosphere to slow us down. So we can continue to burn retrograde, slowing our orbital velocity, to bring both those lines towards the planet and reduce the strain on the ship through friction with the air. After that, we're going to do a few passes. Each pass will slow our ship slightly more so that we don't have to go from 10,000 meters per second down to, the landing speed over the course of a few thousand meters, which would probably kill our astronauts because of the g-forces involved. So instead you do a few passes through and you do what's called aerobraking, which slows down your ship to manageable speeds and allows you to land. Here you can see us doing our final pass over the planet to slow down a little bit more, and on the next pass we'll actually be landing. You can see even on these passes where we're just slowing down, the heat shield underneath the capsule is being heated by air compression of the air, basically. Here you can see our landing run through. As we get deeper into the atmosphere, the air becomes more and more dense, and you compress it more and more as you go, and that heats up the craft. Well, heats up the air, which heats up the craft. That's what the heat shield's for, is to absorb that heating. It's got a ceramic layer on it that chars instead of the craft itself. That will allow us to fall lower to speeds that parachutes can then be deployed without burning up, and those will lower us safely onto the ground. So the red X on the ground represents our expected landing point after friction with the air. And yeah, you can really see the heat generated from re-entry. Little view inside the cockpit showing the forces involved, what it's like. And yeah, as we get lower, deploy drogue chutes. And this just kind of stabilize the craft, keep the right end pointing up, allowing us to slow down a little bit as we descend. So as we get closer and closer to the ground, slow down bit by bit as the atmosphere gets thicker. Parachutes have more of an effect. Deploy larger parachutes so that we can really slow down to a speed that allows us to land without blowing up. And there we go. Landing in the water. Successful trip to the moon and back. First astronauts from Kerbin to land upon the moon. Congratulations, guys.